Start recording. Close that. Open that. We're on page 38. 38. Darn it. Okay. Dear God in heaven, what is wrong with this thing? Okay, let's see if that worked. Okay, the thing is moving now. Good. Okay, so the degree to which an ion affects it, the solubility depends on its concentration. That's where we left off last day. So if we looked at this situation here, we had 0.1 molar calcium ions. We had 0.01 molar fluoride ions. Here we have 0.001 molar fluoride ions, and here we have I'm sorry, that top one isn't 0.1, it's 0.01. So which of these would make it the least soluble? 0.01, 0.01, 0.001, or 0.1 molar?
Probably one of the calciums.
One of the calciums, why?
Because Na is soluble with everything.
Oh, we're not looking at Na, we're looking at fluoride. So we've got the fluoride ion here, we got the calcium ion here. No? D? What do you guys think? Do you agree with D? Do you you said C. Sorry. Okay. My brain is not braining this morning. Do you guys agree with C? Okay, have a chat about it. Which one is going to make this the least soluble? Now, what does it mean by least soluble? Which side of the equilibrium should this be sitting on if it is the least soluble? Sits furthest left. Chat with your neighbor about it.
D is very soluble, but I think it's I don't know. Yes, and we add Ca, we shift to the right hand. So no. That one and we add no wait. That doesn't make any sense. Okay. So it's gonna dissociate just like add Ca. We might have to write the dissociation for all of them.
Anyone have any idea? No? How? How do you not have any idea? It's got to be one of two of them. Which two can we eliminate just by being like, good guessers? Here's our concentrations.
You can eliminate A and B. Well,
We can probably eliminate A and B. Why is that? Because they're the same concentrations. Yes? And not only are they the same, they are in the middle. Oh, yeah.
I just
So now you need to think to yourself, is it going to be a big concentration of calcium that makes it most insoluble, or is it going to be a small concentration of fluoride that makes it the most insoluble? Probably the more one. Because if you increase this more, it shifts to the right, to the left. More. If you increase this a tiny bit, it shifts to the left a tiny bit. Doesn't that make sense? Yeah, okay. So which one is calcium fluoride the least soluble? D. See, you were right. You. Yes, very nice. Okay. So the degree, and we had just said this, the degree to which an ion affects the solubility depends on its concentration. The greater the concentration, the more it affects the solubility. I refuse to believe that so many of you couldn't figure that out. I think there was a lot of not thinking happening. How many people think to yourselves, I'm not asking you to actually, raise a hand or anything like that, but how many of you were just sitting there going, I don't know, and my brain hurts, so I'm not going to think about it? I'd like to wait for somebody else to tell me. Please, Miss Spence, tell me. Please, other person in the class, tell me. If that was you, stop it. It's irritating. Don't be a baby bird. You need to fly from the nest soon. In 2 months, you will be flying free from high school, and you might have to think for yourselves. Okay, so, and if it wasn't you and you were genuinely thinking about it and you just didn't get it, that's fine. It's all good. Okay. All right. The greater the concentration, the more it affects the solubility. Okay. Now, all these preceding examples are just Le Chatelier's principle, but one of these methods is called the common ion effect. It has its own special name, the common ion effect. And that is one where we increase the concentration of an ion. We can shift these equilibria not just by increasing the concentration of an ion. We shifted the equilibrium by decreasing the concentration of an ion. And we could do that by precipitating it. We could decrease the concentration of an ion by adding an acid and reacting an acid with it. We can shift the equilibrium by changing the temperature. None of those things are the common ion effect. The common ion effect is only when you add an ion. I don't know why this one gets its own special name, but it does. Now, why do we call it the common ion effect? It's called that because you add an ion in common with the precipitate. So if our low solubility substance is AgCl, it has two ions. It's got Ag plus and it has Cl minus. You can add NaCl because Na has Cl minus in common with AgCl. NaCl has Cl in common with AgCl. And what happens if we add Cl minus? Tell your partner what happens if we add Cl minus. It's just left. So anytime you add a compound that has an ion in common, it will decrease the solubility. Okay, so we have a decrease in solubility when we add an ion in common. Actually, I shouldn't say by shifting left, by causing a shift left. Okay. We could also have a different ion in common. We could have the silver ion in common. AgNO3 has the silver ion in common with AgCl. Okay, that's what a common ion is. Okay, all the compounds here have chloride in common. Chloride, 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 chloride. So and all of them are soluble, completely soluble, except for the silver chloride. So if you were to add sodium chloride or aluminum chloride or potassium chloride or calcium chloride to the silver chloride, you would decrease the solubility of silver chloride. If I added 0.1 molar NaCl, 0.1 molar AlCl3, 0.1 molar KCl, and 0.1 molar CaCl2 to my AgCl2, or sorry, not AgCl2, to my AgCl, which would decrease the solubility the most?
LCL3.
Yes. Tell your partner which one decreases the solubility the most.
I guess. But it's a balance equation. There's still 3
AlCl3, 0.1, 0.1. What's the concentration of chloride? 0.3. NaCl? 0.1, 0.1. What's the concentration of Cl? 0.1. Which of those is going to make this compound, AgCl, least soluble? Everybody, which one? AlCl3, thank you. I thank you. And I thank you guys for chit-chatting with each other. And I thank you guys for chit-chatting with each other. I don't know what the rest of you all are doing, but I did not see much chit-chatting. And if you already knew, then why were you not raising your hand and saying, oh, I know? For example, AgCl3 is, oh yeah, this is just saying what we already said. No, it's not. If you take AgCl and you dissolve it into a solution that already contains NaCl, so you have a solution that already has NaCl, and you put AgCl solid in there, less will dissolve than would dissolve in water. Is it good? Okay. Does changing an ion concentration have an effect on the solubility? So does changing the ion concentration have an effect on the solubility? Yes. Does changing an ion concentration have an effect on the KSP, the solubility product constant? No. The only thing that changes the KSP is temperature. This is just really highlighting once again how solubility and KSP are two different concepts. They are related to one another, but they are not the same. Okay. So those are the things that will change the solubility of a salt: ion concentration and temperature. What are the things that don't change the solubility of a salt? And if you did the homework, you should know some of them already. Can I change the solubility of silver chloride by adding more silver chloride? No. I'll just have a bigger pile of solid, yes? I cannot make any more dissolve. Can I change the solubility of silver chloride by adding more water? No. More will dissolve, but you also have more volume, so the concentration will end up being the same, okay? So changing the amount of solid, things that do not change the solubility of a salt, adding more water, adding more of the solid salt. So will adding more salt dissolve? Will more salt dissolve? No. The solution is already saturated. You just have a bigger pile of salt. What happens to the rate of dissolving? If you have a bigger pile of salt, what has changed? Surface area is increased. So what has happened to our rate of dissolving? Rate of dissolving increases. Okay, rate of dissolving is like this, increases. What about the rate of recrystallization? And those are going to be down arrows. What happens when we have more surface area? More recrystallization, so you end up with an equal amount. So it also increases. And that's why it's still at equilibrium. They increase by the same amount. And therefore, there's no shift. Will more salt dissolve if you add more salt? Oh, dang. I did them backwards. This should go over here. And this should go over. Yes? Yeah. Maybe I should just be like these. Woo, there we go. Okay, so sorry. So sorry. Will more salt dissolve if you add more water? Add more water. Adding more water does cause the equilibrium to shift to the right as more salt dissolves, but the final concentration of ions will be the same. So you increase the moles of solid dissolved, and you increased the volume of the solution. So the concentration remains constant. So solubility is not changed. Does that make sense? Okay. Does adding more water affect the KSP value? No. Adding more solid, this just talks about what we just talked about. So there's some exercises here you did, 41 and 42 yesterday. This is what's going to be on the quiz on Tuesday. Quiz Tuesday on 3.2. Okay. So there's more practice here on page 43. And then there is more practice here. Look, extra practice, changing the solubility. Yeah, so you have lots of practice changing the solubility. You will also be responsible for stuff from 3.2a, like being able to say define solubility, right? Being able to relate the KSP to the solubility if you have compounds with the same ratio of ions. If you remember, we had, where is our one there? There we go. We had some compounds that were all 2 to 1, 2 to 1, 2 to 1, 2 to 1. Whichever one had the biggest KSP was the most soluble. Yeah? Okay. Is there anything else in there? No, really, it has to do with the common ion effect. It has to do with decreasing ion concentrations, either by adding an acid that reacts or by adding something that precipitates, and knowing that adding water and adding solid does nothing. This is a short quiz. Short. Like it will take, I'm guessing it'll take 5 minutes. Okay, short quiz. But it doesn't really fit with the other quiz, and the other quiz is long, so the math quiz. So let's move on to some math. Why don't we? We already did solubility to KSP. Before we carry on a little bit further, we are going to go back and do on page 48 some dilution calculations, because I find that people have forgotten that a lot from grade 11 generally. Okay, so we're going to review dilutions on page 48. So the key idea in dilutions is that diluting just involves adding water or another solution. So basically, you are just changing the volume. You are only changing volume. The number of moles of solute stays the same. So hopefully by this time you're familiar with this concept. We did a little bit of this yesterday. If we start with 1 liter and then we add another liter, we end up with 2 liters. If we started with 2 moles of solute, if one of these little doodads represents 1 mole, we have 2 moles in 1 liter. If we add that 1 liter of water, we have not changed the number of moles, right? They didn't know moles came from anywhere. We still just have the 2 moles. But now it is in 2 liters. So now we have 2 moles in 2 liters, and then that's going to equal 1 mole per liter. And so you need to be good at doing those calculations. They're not always going to be as nice as, add 1 liter to 1 liter. So the most general way that will always work for doing dilutions is to, number 1, find the moles of solute. And then number 2, you're going to divide by the new larger volume. Right? Because here we were like, oh, I've got 2 moles of solute. It is now in 2 liters. 2 divided by 2 is 1 molar. So if we have an example like this, 2 liters of a 9 molar solution of NaCl is diluted to a final volume of 6 liters. Find the new concentration of NaCl. Do you know how to take these 2 numbers and find moles? 2 liters times. What does capital M mean? Moles per liter. So if you're showing your work, you can say that's going to be 9 moles per liter. Now you have liters on the top and liters on the bottom. Those cancel out and you get 18 moles. Okay, so that's what we've got here. We've got 18 moles. Our new volume is 6 liters. So our 18 moles is now no longer in 2 liters. Now it is in 6 liters. So we take our 18 moles, divide by 6 liters, and we get our new concentration, which is smaller than it was before. We started at 9 molar and we finished at 3 molar. Is good? Okay. This will always work. And this will work no matter what your ratio of ions is, no matter if you're mixing 2 solutions that both contain chloride. If you find the moles of chloride here and the moles of chloride here, and you add up all your moles of chloride and you divide by your total volume, this method will always work, okay? There is another method, there's another situation where we use dilutions, and this is actually used a lot in lab work. Often in the back room there, we will have something called a stock solution. A stock solution is more concentrated than we would usually want to use. Okay, so for example, we have 12 molar HCl. That's a very, very concentrated strong acid. Do you think you're going to be wanting to work with 12 molar HCl? Do you think as a teacher it would be like good for me to have you working with 12 molar HCl on a regular basis unless there was a really good reason for it? No. So instead of doing that, we're going to take that 12 molar or whatever it is and dilute it to the concentration we want. Maybe it's 0.1 molar. And we need to figure out how much of the stock do I need and how much water do I need to add to it to get whatever concentration we want. So again, do you remember back here we were like, find the moles of solute. For this style of question, you are also going to find the moles of solute. Thank you so much. Yes, find the moles of solute. And then, in this case, you're being asked what volume of the stock solution do you need for that many moles? So what volume of the stock solution contains that many moles? So for example, if we want to make 2 liters of, and we've got our little particles again here. So the concentration of those little particles is 2 molar. That's our stock. No. What is wrong with the, oh, that's not working. That's why. That's okay. Yeah, I've had an electrical problem with that power bar. And I need to remember that. I can't plug things in there. They won't work. Okay. All right. Sorry about that. So we want to make 2 liters of of that. That's what we want. This is going to be our new concentration. This is our diluted concentration. And we are starting with our stock solution has a concentration of 8 molar. So that's our big concentration, and we want to get it smaller. How much of the stock solution in liters will we need? Any dilution problem, the first thing you're going to do is find the moles of solute. What numbers could you use here to find the moles of solute? We have 3 numbers, 2 liters. We have 2 molar. And we have 8 molar. To find moles, yeah, these two numbers are connected to each other, yes? We have 2 liters of this, so those two are connected. So you can find your moles by saying we have 2 liters. Oh, by the way, you should use this all the time. The word of means, do you guys know? Of means times. Times. 2 liters of. 2 liters times of 2 molar. 2 moles per liter. So if you're ever doing a dilution problem and you're like not sure which ones to multiply, look for 2 numbers connected by of and multiply them. The unit should work out. So if we want to make 2 liters of 2 molar, we need 4 moles of whatever that is. Yes? We can look at a little picture and say, I need 2 liters. So if that entire volume is 2 liters, then each half of it is 1 liter. Yes, so we have 1 liter and a 1 liter. And each liter is 2 moles per liter. So there's 2 moles in this top liter, and there's 2 moles in the bottom liter, and that gives us 4 moles, which we did by just doing the math. Obviously, you're not going to draw this out every time, but that's really where the math comes from. So now we know this is how much we need. Where are we going to get those 4 moles from? From which solution? We're going to get it from the stock solution. So now we've got a stock solution, and over here we have this entire thing is 1 liter, right? And it is 8 moles per liter. So in that 1 liter, there are 1, 2, 3, 4, 5, 6, 7, 8 moles in the 1 liter. How much of that volume do we need to get 4 moles? We need a half a liter. Half a liter will contain the 4 moles. How do we do that math? You'll say 4 moles, and this is when it's important to write it out like this, 8 moles per, ooh, what was that? That's not an L. Moles per liter, because you can now multiply. You want the moles on the bottom and the liters on the top. And where does the 8 go? The 8 goes with the moles, okay? And that gives you 4 divided by 8, which gives you 0.5, which is half liter. So you would take a half liter, and then you would dilute it up to a final volume of 2 liters. So you would take your little half liter there. And you would add 3 liters of water. Why is it 3? We're adding 3 liters of water. Oh no. Ugh. 3 halves of liters. 1.5 liters. I'm so sorry. Thank you. You're adding 3 times 1/2 liters of water. In other words, 1.5 liters. So now we have a total volume of 2 liters. We have 4 moles in 2 liters total. So that's going to be 4 moles in 2 liters. Did we get our 2 molar? Yes, we did. Okay. Now this is complicated. There's a lot of pictures and things, but I would like you to be able to visualize it so you kind of know where it comes from. However, you might not want to do that thinking all the time. Yes? So we might want a simpler way of dealing with this. So first simple way is just to remember, always find the moles and then use the moles to find either volume or molarity as required. Or does this formula look familiar to anyone? M1V1 equals M2V2? Anyone? Oh, wait.
I use that in the law.
You might have seen it as C1V1 equals C2V2. Concentration 1 times volume 1 equals C2V2. I personally, actually, I hardly ever use this formula because I find I get my numbers in the wrong place and I get them upside down. And so I like actually being able to think through it. But if your brain doesn't like thinking through it, this might be a good little savior for you. Okay? So M1 and V1 are the variables for the initial concentration, M1, the molarity, and the initial volume. M2 and V2 are the final concentration, the molarity and the volume. Now, if you're interested in why this formula works, we are multiplying on the left-hand side M times V, molarity times volume. Hi, Tony. Come on in.
Tony.
It's okay, come on in. Tony has questions. So molarity times volume, we've got molarity is moles per liter times liters, and you get moles. Yeah? MV gives moles. So MV is moles. When we dilute something, what happens to the number of moles? It stays the same. Okay? So that's why moles 1 is going to equal moles 2. Moles before is equal to moles after. The initial volume times the initial molarity is the moles before. These are M1V1 is moles before, M2V2 is moles after. What's your question, Tony? Sure. Oh, okay. Maybe we should wait then. Ask Taranya, see if he can help you. So you can use that in any situation, and as long as you can identify what the initial volume and the final volume, the initial molarity and the final molarity are, you can solve, okay? Then you have one unknown and you solve for it. There's another method, and this is the one that I like, but I don't know, I grew up with it and it makes a lot of sense to me because fractions make a lot of sense to me. right? So when we did our dilution, when we added two equal volumes, we doubled the volume and therefore the concentration was 1/2. Yes? And if you quadruple the volume, the concentration is going to be 1/4. Yeah? And that little fraction here is going to be the old volume over the new volume. We went from 1 to 2 when we had a 1 and a 2, 1 liter to 2 liters. The concentration got halved. If we go from 1 liter, 4 liters, the concentration gets multiplied by 1/4. It gets quartered. If that makes sense to you, that's fabulous. If it doesn't, that's okay too. You can still use this method if you want to. I call it the noon method because if we read from left to right, we have our new concentration is equal to our old concentration times our old volume over our new volume. So it's concentration, concentration, volume, volume.
Divide it.
It's actually this same formula just rearranged. Yeah. Okay. To me, it makes a little more sense because M1, V1, M2, V2, everything just seems to be floating around, but that's just me. You may love that, which is great. So how do I remember that it's new concentration and old concentration? C comes before V in the alphabet. So it's concentration, concentration, volume, volume. Concentration, concentration, volume, volume. I don't know. If you don't like it, don't use it. So let's try solving this problem 3 different ways. If 45 milliliters of water is added to 250 milliliters of 0.75 molar, oh, look, we've got that word of. What does of mean? Times. Oh.
Wait, do I have to change it into liters?
You need to change that into liters. Okay, so that's going to be 0.250. Liters. And I would always rewrite my molarity as moles over liters, 0.75 moles over liters. And of means times. And what am I solving for? I'm solving for the moles of K2SO4. Point 0.25 times 0.75. 0.1875 moles. You guys figure out what to do with that number next, and then try the M1V2 equals M1V1 equals M2V2 while I go and see what's happening over here. What's that? Oh, this one here? There's 2 things that failing to be plastic polymer causes the magnitude of the experimental value of to large. So basically, yeah. The magnitude of the experiment. Okay, so you have calculated the Q from the experiment. That's the experimental Q. Yeah, yeah. Okay. So that's not the theoretical one, it's the experimental value. And so what we've done is we've said, okay, theory solvers. transferred. Heat transfer from reactor here, right? Yes. From the reaction. I don't know. Let's just run this again. Okay, doesn't. Okay, so. If it's the other way around. Yep. Now. Delta T. So if we have, is that correct? Yeah, so what's happening here? But so if it's not MC is too small. Less than that. Yeah. Water, oxygen, plus, yeah. And now we don't have that. So we have said. No, it's not the question, it's my writing that. No, but it's just that our city got changed. We think that all of them are water. Right. We think all of water. Rather than 9.5. Yes. So so the temperature of the water changes by capacity. Yes. The temperature changes less.
Did I do it wrong?
And then we think it is. Okay. Yes. Yes, delta is less. Then it would be.
Because
If there were no power there.
There is power delta T would be less. Because
With power there, with power there. It's less. Okay, okay, okay. So, yes, our delta is smaller. Oh, in how yes. Is it too wrong? Oh, God bless.
But it's always don't have to explain. You confuse me too.
What did you guys get for this?
0.635.
Yeah, the concentration of K2SO4, and you should show it this way. This is how you should show your work. You should say concentration of K2SO4 if you want to say that that is diluted. You can say DIL for diluted, or you can say nu if you want to. Okay, that's going to be equal to 0.1875 moles over, what's our volume?
Total volume.
0.295 liters. Do you guys know why it's 0.295 liters? Because we added the two. Excellent. 0.295 equals 0.656 molar. And that would round to then 0.66 molar. All right. Phew. M1, V2, M2, V2. Did you guys have any issues with that? Shall we do it? Okay. So this is M1 and this is V1. And you do not need to change out of milliliters to do M1, V2, M2, V2, okay? So, and V2 is 45 milliliters plus 250 milliliters. So our unknown is M2. So I'm going to solve for M2. M2 is equal to M1 V1 over V2. M1 is 0.75 molar. V1 is 250 milliliters. V2 is 295 milliliters. Do you see why we don't need to change out of milliliters? Because the milli cancels with the milli. Okay, and we get 0.66 molar. The Noon method, we say, what is my old concentration? 0.75 molar. What fraction am I going to get? Well, I start with 250 milliliters and I finish with 295 milliliters. And I get 0.66 molar. It is essentially the same. You will notice, though, that if you carry on with chemistry, this here is known as the dilution factor. And it is the fraction. It's the volume fraction. Anyway, you don't need to convert to liters when you're using M1, V1, M2, V2, or Noon. Okay?
Did we convert into liters first?
No, it'll give you the same answer because you'll just multiply the top by or you'll divide the top by 1,000 and you'll divide the bottom by 1,000, so they'll both be divided by 1,000. Okay, so we only have we got 5 more minutes. Okay. Here's how you actually make a diluted solution. So this is your stock here, stock. And you'll measure out a certain amount. You'll have to have calculated that. You will transfer it into a new container. And the rest of the stock just goes back on the shelf. So this is our stock, small volume. And then we add solvent. Until we get to, there's usually a mark on these things, and that's going to be our final volume. Do you guys know what all these pieces of equipment are called? A pipette that only has one mark on it is called a volumetric pipette. A flask that has only one mark on it, can you guess what it's called? A volumetric pipette is a pipette with only one volume marking. Where did my eraser go? There it is. Okay. A pipette with only one volume marking. What would we call a flask with only one volume marking? A volumetric flask. Okay, so we've got a volumetric pipette, we've got a volumetric flask. You'll notice that both of them are very skinny. Yes, we have a skinny neck, and that's where the mark is. The volumetric pipette, the area where the mark is very skinny. Why do we want it to be very skinny when we're measuring a volume? It's more precise. You know, like if you had a wide neck, if you add one drop, it won't change the height very much. But if you have a skinny neck, one drop will change the height quite a lot. So you'll be able to get your volume much more precise. So if it's skinny, you get a more precise measurement. So basically, take your stock solution, however much contains the right number of moles. So you take your stock containing the correct number of moles, and then you just add water. I'm going to put water, technically solvent, but we're going to only be using water. Add water to the mark. When you get really, really close to that mark, you should not pour with a beaker anymore. You should, and in fact, you shouldn't even use the wash bottle anymore. You should, once you get to about here, you should use the wash bottle. And then when you get really close, you should use what's that called? This is called a wash bottle. What's this called? That's called a dropper or medicine dropper. Nope. Sometimes it's called an eyedropper, a medicine dropper. We can just call it a dropper. Okay, you would then stopper the flask, which means put a lid on it, and then you invert it. Never, ever, ever tell me that you flip it. Do you guys know what to flip means? Flip. Yes? Do you want to flip a volumetric flask? Oops. If I flip things, they end up on the ground because I have no hand-eye coordination. Anybody want me to flip my volumetric flask? No. We invert it. Turn it upside down, not flip. All right, let's figure out what to do for homework. Today you are going to do page 43, I think. Yep, page 43 and 43, 44, 45. If that's too much, just do 43, 44. Okay? Yeah. Yes. Yes.
I did a mod for
Absolutely not.
it can be easier once you can build the stuff because I was thinking about this stuff. Yeah, but. Most of the each seed is better. That one could be that all.
Nice. Last minute.
Bring me some half.
You would think I could study for both? Hell no. I'm not